There are many different events in the lifetime of an organism, and they can differ in terms of what events happen and in terms of the timing with which they happen. When these are all put together, it's referred to as a life history strategy. And if that term, strategy, sounds like the sort of thing you would use to, say, win a game, that's a reasonable description of what it means. The life history strategy of an organism is a set of life history traits that natural selection optimizes in order to maximize the reproductive output over the lifetime of an organism. In other words, to maximize the number of offspring that an organism can leave behind. The life history events that influence lifetime reproductive fitness include things like the time of hatching, the speed at which an organism grows to maturity, which often trades off against its size at maturity. The final size at maturity, of course, may matter for things like the allocation of resources. Larger organisms can allocate more resources to offspring. Parental care, by the way, is a resource that can be allocated to offspring. So all of these life history events, these life history traits, are intertwined. And what natural selection has to do, basically, or what natural selection tends to do, rather, is it favors the combination of events, the combination of timing and nature of these events that maximizes individuals' ability to crank out offspring for the next generation. All of these events are at least partly, usually partly influenced by genetics, and so they can evolve, although a lot of them are influenced by non-genetic factors as well. So, for example, the amount of food that an organism gets is going to influence its final size at maturity. So when you see an organism's phenotype and you see its life history out in the wild, what you're partly seeing is genetic influences, what you're partly seeing is environmental influences. But because these traits are partly under genetic control, they can and do evolve. Human beings have a really extraordinarily simple life cycle. We start out looking quite different than we do as adults, but it's just sort of one life stage that grows and changes a little bit as it grows, but largely stays looking the same all the way to adulthood. Many other organisms have much more complicated life cycles. So for example, there are organisms that go through metamorphosis, that is, they have a shape change somewhere in their life cycle. For example, this is the larval stage of a sea jelly, a planula larva. It metamorphoses into a hydroform, which then grows into an adult colony. That form then gives rise to what's called a medusa form. So this polyp here grows and buds off lots of different individuals. That, by the way, is very different than human beings because this is a modular growth form rather than a unitary growth form. All of these sort of different events, the metamorphosis, the different life forms, the colonial growth form, these are alien to us. But a lot of organisms do these sorts of things. They have much more complex life cycles than we do. You're probably more familiar with something like this organism, this butterfly, but it also has some life stage changes. The resting stage is the egg. From there hatches a caterpillar. The caterpillar goes through another resting stage, the pupa, and the butterfly emerges looking radically different. And of course, this too is an example, probably one that's more familiar to you than the sea jelly, of a life history that's more complex than the life history of human beings. Okay, we've been talking about the growth of populations. And as I mentioned before, we made a lot of assumptions about the individuals in those populations. So for example, we assumed when we're doing the exponential or the logistic equation that basically all individuals in a population are the same. We kept track of births and deaths in a population, but we assumed that all individuals had the same possibility of giving birth and that all individuals had the same probability of dying during each time step. And of course that isn't true. When ecologists really want to know why a population is growing or shrinking, and they really want to do something about it, they study birth and death in a more detailed way, a way that takes account of the differences among individuals, particularly with respect to their sex and to their age. What's shown here is what's called a life table. And this is a chart that keeps track of birth and death over the lifespan of a number of individuals. In this particular case, yes, we're again back on Daphne Island in the Galapagos, and we're looking at Darwin's finches. In this case, it's Geospiza scandens. And this is probably the data of the Grants or one of their collaborators. But what this life table started out with is a cohort of 210 individual finches. A cohort is a group of offspring that are all born at the same time. And in this case, what happened was that cohort was tracked forward through time. Generally, life tables are made only using data from females. Sorry, guys. The reason for this is that only females do the reproducing. They're the ones that crank out the kids. It's true that fathers do donate some genetic material to offspring, but it's easier to keep track of which females of which ages are giving birth. So often, life tables will only track females. The data that are shown here may be a little bit confusing to you, but the basic data that is tracked and collected by ecologists is found in these first two columns. There's the age in years, and there are a number of individuals alive. So we start with 210 finches. That's the number that hatch, that make it to the age of 0. Then what's recorded here is that 91 of those individuals make it to the age of 1. Of those 91, 78 make it to the age of 2, and so on. And I think you'll notice the trend in this number here. This number always goes down because individuals that die at one of these ages do not come back alive again the subsequent age. That only happens on Easter, and that was a long time ago. There are a couple of variables that we get from these data that you ought to be aware of when you're looking at a life table. The number we're really interested in here is this one, survivorship. Okay, and this is this has a very specific definition that you should know. Survivorship is the fraction of individuals that are left alive from the individual cohort, from the original cohort at any particular time. And it's usually denoted with the lowercase letter L. So this number here would be L sub 0, L with a little subscript 0, and it means the survivorship at age 0. The survivorship at age 0 is never interesting because it is always 1. 100% of the individuals that are born survive to be born. Okay, this number here is much more interesting. It's 0.434. That's L sub 1. That's the survivorship of individuals from age 0 to age 1. If you needed to calculate that, you'd simply divide the number of individuals alive at age 1 by the number of individuals that were originally in that cohort. So 91 divided by 210 is 0.434. You can keep on calculating survivorship values for every age that some individuals are still alive. And each time what you're doing is you're dividing each one of these numbers by 210. So 0.295 is 62 divided by 210. 0.2 is 42 divided by 210, and so on. And obviously there's a trend here. This number always goes down over time and never comes back up. So survivorship is actually the number that you're really interested in when you're looking at a life table. I should point out that there are other numbers here. Survival rate is what's shown over here. And that's the fraction of individuals that make it from one age class to the next. So for example, if you're thinking about the number of individuals that make it from age 1 to age 2, that number is 0.857. So 85% of these 91 individuals make it to age 2. To get that, you divide 78 by 91. That's a very different quantity than the survivorship to age 1. Okay, so do not get these two things confused. Mortality rate, by the way, mortality rate here is just 1 minus the survival rate, so that's pretty straightforward. But you can look at, it's sometimes easier to look at mortality rate and see basically when are the age classes when most individuals die, than it is to just look at survivorship. And that's why often life tables will contain this information. So what we have here are some columns of numbers, which may be pretty hard to understand. These, when you look at these numbers, they may not have a lot of intuitive meaning to you. I mean, you can see clearly that most individuals die pretty early. About half the population doesn't make it to age 1, and then you get diminishing survivorship as you go on down until finally no finches make it past the age of 13 years. But there are other much more useful things we can do if we have this kind of information. One of the things we can do is plot what's called a survivorship curve. And these are different examples of survivorship curves up here. Survivorship curves show basically survivorship over time. Usually survivorship is plotted on a log scale over here. And you've got time in some unit down here. So for example, for human beings, you probably measure age in years. For birds, probably years as well. But in things like this is a weedy plant, we would measure its age in months. Different shapes of curves reflect what are called different life history strategies. And we'll talk about this a little more later. But you can see that they're really very different shapes into these three curves. The one over here, where there's very little mortality until the end of the lifespan, is called the type 1 survivorship curve. This one, where survivorship, more or less, it follows a constant slope down until all individuals are gone, that's called a type 2 curve. And over here, with this plant, you see what's called a type 3 curve. Lots of mortality early on, and then survival stays constant for a while and then drops down again at the end of the lifespan. On the quiz questions, you're going to be asked a couple of questions about what kinds of organisms probably have these different kinds of survivorship curves. So before you start the quiz, and maybe you want to do this right now, you'll want to stop and think about what kinds of organisms might have these different patterns in terms of their mortality.